problem 11.7 comes where the non-spherical potential is given, and this that the wave is and the particle is initially traveling along the z-axis, and it comes under the non-spherical double delta function. And here you can see the vectors are mentioned, and it is also mentioned that is non-spherical potential. So here they also told us that k here is the unit vector in z direction. So we'll treat k vector here as a unit vector, while the r vector is equals to x I hat plus y j hat plus z k hat. Okay, so if we want to write v of r prime in terms of x y z, then how we'll write that? I'm taking v naught common, so this is a three-dimensional spherical delta function. Here in place of r prime I'm writing x I hat, in I will put hat right there so that you may know. It is properly mentioned that k vector is a unit vector, that is why I'm treating it as a unit vector. Minus a k vector minus delta. Here since it is a non-spherical potential, that is why we'll have to use the volume integral, and in volume integral we'll take dx, dy and dz. That is why I'm resolving it into xyz forms. Now we can write the similar unit vector like this is xi hat plus yj hat. Here the k hat is common, so we can write it as z minus a k hat. Okay, minus sigma into xi hat plus yj hat plus k hat can be taken as common, and here it is like that. Now the resolution of r into its component will be like that: x, y and z. Means the coefficient corresponding to I, j and k will be mentioned here. In case of r alone, the coefficient to I, j and k are simply x, y, z. That is why x, y, z, that is why I wrote it like that. Now if it is like the coefficient of I is x, then we'll write it as sigma of x. We'll separate the delta function into their components into different x, y, z coordinates. So then the coefficient of j vector is y, that is why I wrote y here, and the coefficient of k vector is z minus a, that is why I will write z minus a right there with negative sign, and then sigma x as it is, sigma of y, then sigma of z plus a, because the coefficient of k vector is z plus a right there. So this is the potential in terms of x, y, z components, and we have resolved the x, y, z parts, because during the integration we will do the integration of, since it is not a spherically symmetric potential, that is why we have to take the volume integral in dx, dy and dz forms, and for this the integrand should be in x, y, z components also, it should not be in other coordinates, and for that reason we have to convert our potential into xyz parts, and luckily they are all separable, and now our integration will be very easy. By separable I meant that the potential term has explicit form, means the x dependence is completely separated, y dependence is completely separated from all other components, like it is delta of x, not delta of xy and all that thing. So the integration will be very easy, as we will see later. That is why I just separated the delta function that contained all these functions intermixed into separate functions. Now the expression for the scattering amplitude, we need to find the differential cross section. For this I'm first finding the scattering amplitude, and its formula is minus mu by 2 pi h cut square integration, this is volume integration, and v of r prime okay. So we'll in next step write it like that. dx, dy, dz, and there will be three integrals corresponding to it, and they will run from minus infinity to plus infinity, because this is a volume integral and it will run from throughout the space. And for xyz, these minimum and maximum limits are minus infinity to infinity. Now we'll put the value of v of r prime right there, and before we do that, we have to write this dot product, and for this we need to find q dot r prime. Now q is qx, I had qy. Here x and y are in subscript. There is a better way to do this, is to take the component of q corresponding to x direction as q1, this one q2, and this one q3. Okay, that will make the things easy for us, so that we may not confuse with subscript and the normal variable forms. And now this dot product comes out to be q1 x plus q2 y plus q3 z. These three things will come right there, and we know that the things that are like adding to each other in exponents, they can be separated with the common base, and the thing that comes out will be like that. So that this one part will go to the to the integral that whose integration will take place with respect to x. This will to the y1 part, and this will go to the z part. Now I'm putting the value of v of r prime, this one expression right there, and we get minus infinity to infinity. I will separate the integral later. First of all, I will put the value of v of r prime, which was this whole thing. So v naught delta x. I hope you can solve this very easily, because this is very easy integral, because it involves delta functions, and this is the value of potential, and the exponent term that comes here is q1x, q2y, q3z, and dx, dy, dz. Okay, this is the whole integral. I'm writing this expression with this expression, okay, and the integral will come with it. Another integral with negative sign here, and this three integral will come along. Then these delta functions, and these three terms. Then dx, dy, dz, and the brackets closed. Now we will separate the integrals into x parts. For the x part, there is a delta x, and this exponential thing dx. Another integral with y part dy. Then the z part is partial delta z minus a and dz. Now I have wrote this integral into separate forms with x integral, y integral, and z integral. Now this one integral will be done the same way. And dx minus infinity to plus infinity. And here partial z minus a e to the power iota q3 z dz. Okay, now we need to solve this integral, these integrals, and you all know what will be the solution to this. Here for this one term will remain as it is. Now for those who don't know about the integration of functions that involve delta function in them, I'm just giving you an idea. about the integration, whatever the limit of integrations are, okay, irrespective of limits of integration. If there is a delta function, let's say, and it is a function of r minus some constant, let's say the constant is t, okay, r minus t, and I'm taking it in x form, okay, so that if even if it is an r variable, the same rule applies. And here is a function which is dependent upon r also, okay, and there is a function besides delta function that is a function of r also, and the integration is taking place with respect to r variable. Then the integration of this whole term will be equals to we'll put this one term equal to 0, and we will find out the value of r that we will get. This is the property of delta functions, and that is why it is possible. This is a consequence of one of the properties of delta function, that they are only defined at one point, which is r is equals to d, and for all other points they are 0. That is why the integral is only non-zero for r is equals to d point. And this is now the integration of this integrand will be equals to the value of g of r at r is equals to d. So its integration is simply, we'll put r is equals to d in this function that is besides delta function, and that is simply the integration of this whole integrand. Now this can come in various forms, okay, you just need to put the that function whose delta function on which the delta function depends, okay, the function here is the main variable on which delta function depends and which decides what kind of delta function is. So put that equals to 0 and find out the value of that variable, and put that variable into the function which is besides delta function. That function could be 1, could be 2, could be any constant or any variable that depends upon r, okay. So now let's see what is the integration of the terms that we are writing in this problem. The integration of this term will be, you need to put the value of x equal to 0, and this is the value of x that you need to put in this expression that is besides the delta function, and that will simply the integration of this term that is 0. So if you put x is equals to 0 in this exponent, this function q into 0, then it will make the whole exponent 0. So e to the power 0 is 1, so this one term will become 1, this one becomes 1 2, this one becomes 1, and this one becomes 1 also. The only known one value that comes that results from this integral is this one and this one. For this you put value z minus a equal to 0, and the value of z that you get, that you have to put in this function is a. So you will put e to the power iota q3a. This is the value that you will get, and here you need to put, here z, it's z plus a here, okay, I by mistake wrote z minus a here. So you will put z plus a equals 0 and z equals minus a is the value that we will put in this expression. So whether the limits are minus infinity to infinity or whatever the limits are, always the integration of the function that involves delta function besides it is always done the same way. The function that is besides the delta function, you have to put the value of the variable that you got from this type of thing, and you put it into the function, and this is simply the integration of that integral. So it will be e to the power iota q3z, which is minus a, so it is e to the power iota q3a, and here is the negative sign, okay. So here will be the negative term, here will be the positive exponential term. So I'm simply writing it right there. And here the result was iota q3z minus a e to the minus q3a, and if we divide it by 2 iota and multiply it with 2 iota, now this expression by Euler's identity is equals to sine q3a, okay. So this is the value f of theta, Now we need to find out the differential cross section, and that is equal to the square modulus of this scattering amplitude. If you don't know how to apply the Euler's identity, if the two exponential functions with powers as positive and this is negative, but they're like these things are equal to each other, q3a, q3a are equal to each other, but here is positive iota and this is negative iota, this is negative power, and both of these are like subtracted from each other and divided by 2 iota. This whole quantity is equal to sine of this equal term, which is q3a. So I wrote it like that, in that way. So here 2 and 2 gets cancelled out, and minus v naught iota pi h cut square sine q3a of this quantity is, we'll replace iota with minus iota and it becomes this. It multiplies with negative and it becomes like that. We need to multiply both of these quantities to get the differential cross section, and what we get is mu square v naught square iota square will be minus 1, that multiplies with this minus and it becomes positive as a result. So this is the answer.